In this lecture, we study LP spaces. So, topics of this lecture are following: LP spaces, where P is real number strictly greater than 1. So, the main theorem we will prove here. So, this is the main theorem. So, this is the main theorem. So, we prove that LP comma this function, this pair is a non-linear space. So recall that what is LP? LP equal to set of all sequences x n, or x equal to the sequence xn, x equal to xn. So real sequence xn belongs to R, n belongs to set of all naturals, such that summation xn absolute value of this power p summation over n equal to 1 to infinity. This is finite. So this is LP, and what is the function? This function sub p, this is function with domain LP, and this is real valued. So codomain is R, defined by x sub p. So this is equal to summation absolute value of xn power p, or summation over n equal to 1 to infinity whole power 1 over p. Okay. So this is, so basically we prove that this is a non-linear space for every p, real number p, which is strictly greater than 1. So to prove this main theorem, we have to prove the few inequalities. First, we prove that for a and b greater than or equal to 0 and p real number greater than 1, we prove that a plus b whole power p, this is less or equal to 2 power p times a power p plus b power p. Then we will prove in Young's inequality, Holder's inequality, and Minkowski's inequality, and finally we prove the main theorem. Okay, so let us prove this inequality first. So here is the statement: let p belongs to the open interval 1, infinity, and a, b, these are non-negative reals, then this inequality holds true. Okay, so here is the proof. So first, for every a, b non-negative reals, what we have, a plus b, this is less or equal to a if a is greater than or equal to b, and to b if b is greater than or equal to a. So if a is greater than or equal to b, so here we replace b by a, then what we have, a plus b is less or equal to 2a, and similarly a plus b less or equal to 2b when b is greater than or equal to a. And therefore what we have, this whole power p, this is less or equal to 2a power p when a is greater than or equal to b, and similarly this power p when b is greater than or equal to a. And what is this? This is equal to 2 power p times a power p, and this is equal to what? A 2 power p times b power p, 2 power p times b power p, and this is less or equal to 2 power p times a power p plus 2 power p times b power p. So we are adding this extra non-negative term, so the right hand side is greater than or equal to the left hand side, and similarly this is less or equal to 2 power p times a power p plus 2 power p times b power p. So in either case, when a is greater than or equal to b, or b is greater than or equal to a, what we have, a plus b whole power p, this is less or equal to this common quantity. Okay, so this implies a plus b whole power p. This is less or equal to, so let us take 2 in common. So this is equal to 2 power p times a power p plus b power p. And here also this is equal to 2 power p times a power p plus b power p. So what we have, this is less or equal to 2 power p times a power p plus b power p. So this is the proof of this inequality. Okay. Well, next we prove Young's inequality. So here is the statement. Let P belongs to the open interval 1 comma infinity and Q is some positive real number satisfying this equality. 1 over P plus 1 over Q, this is equal to 1. Okay. Then the theorem says that for any a comma b non-negative real numbers, we have a times b is less or equal to a power p by p plus b power q over q. Okay, so this is called Young's inequality. So let us prove this inequality here. So proof. Okay, so let us consider this given equation. 1 over p plus 1 over q, this is equal to 1. And this implies 1 over q, this is equal to 1 minus 1 over p. And what is this? This is equal to p minus 1 over p. Okay, so what we have, this implies q equal to p over p minus 1, and this implies q minus 1, this is equal to right hand side minus 1, that is equal to p minus p plus 1, that is 1 over p minus 1. So what we have, p minus 1, so this is equal to 1 over q minus 1, and q minus 1, this is equal to 1 over p minus 1. So this is what we have. Now we consider the following function y equal to x power p minus 1. Consider y equal to x power p minus, power p minus 1. And so then what we have, then x equal to y power 1 over p minus 1. This is equal to, this implies x equal to y power q minus 1. Okay, so now so suppose this is the point A and this is the point B. So if you integrate the function x power p minus 1 dx over integration over 0 to a, so then what is this? This is the area. So this is the area, okay, bounded by this curve and x-axis and the line x equal to a. Okay, so this is the area, and similarly plus 0 to b y power q minus 1 dy. So what is this? This is the area of this region. So bounded by the curve y equal to x power p or x equal to y power q minus 1, and the line x equal to b and y axis. So this is the area given by this integration. Okay, and which is greater than or equal to AB. So what is AB? AB is the, so AB, what is AB? AB is the area of this region. this quadrilateral. Okay, and therefore AB is always less than or equal to sum of these two areas. So what is the extra term here? In the right hand side, this is the extra area. So in the right hand side. Okay, so and this implies AB is less or equal to A power P over P. So value of this integration is A power P over P, and value of this integration is B power Q over Q. So which is nothing but in Young's inequality. Okay. And furthermore, equality holds if and only if B equal to A power P minus 1. Equality holds if and only if B equal to A power P minus 1 or A equal to B power P minus 1 or equivalently this. Okay. So this is called Young's inequality, right? So now we prove so Holder's inequality. So before going into the Holder's inequality, we have a remark here. So remark, let me change the color. For P equal to 2 and Q equal to 2, so 1 over P plus 1 over Q, that is equal to 1. So for P equal to 2 and Q equal to 2 in particular, for these values, Young's inequality gives geometric mean is less than or equal to arithmetic mean. Young's inequality gives geometric mean less or equal to arithmetic mean. So what is that? So if you put P equal to and Q equal to 2 in Young's inequality, what we have AB less or equal to A power P, that is A square over P means 2 plus B square over 2. Okay, and this implies to a B, this is less or equal to A square plus B square, and this implies A square plus B square minus 2AB. This is greater than or equal to, or okay. So from here what we have, so this implies 4 times AB. This is less or equal to A square plus B square plus 2AB, and this implies 4AB less or equal to A plus B whole square, and this implies AB less or equal to A plus B over 2 whole square, and this implies square root of AB. So A and B, these are non-negative or real numbers. So this implies AB square root. This is less or equal to A plus B over 2. So this is geometric mean of non-negative real numbers AB, and this is arithmetic mean of non-negative real numbers A and B. So this implies GM less or equal to AM. So geometric mean is less or equal to arithmetic mean. Well, now we are ready to prove Holder's inequality. So let us state as a theorem. So let us label the theorems. So this is 2, theorem 2, and here we have theorem 3. Let P lies between 1 and infinity, and Q in R greater than 0, satisfying 1 over P plus 1 over Q is equal to 1. Given that X belongs to L P and Y belongs to L Q, then we have so what is X? X is nothing but the sequence Xn. N belongs to set of all naturals, and this is equal to Yn sequence Yn. N belongs to set of all naturals. Okay, then what we have summation absolute value of Xn times Yn. Okay, summation over n equal to 1 to infinity. This is less or equal to P norm of X and times P norm of Y. Okay, so we prove this theorem. So proof. So we apply Young's inequality here. So by Young's inequality, what we have X I times Y I, absolute value of this is less or equal to Xi, absolute value of this power P over P plus Yi, absolute value of this power Q over Q. So we have this inequality by applying Young's inequality. Now we have Xi times Yi over P norm of this times Y Q norm of this. So absolute value of this quantity, this is less or equal to Xi. So again here we are using Young's inequality for P over X, this norm of P norm of this. So for P whole power P, so times 1 over P, this is plus 1 over Q times absolute value of Yi power Q over norm of Y Q norm of this part Q. Okay. So again by Young's inequality, we have this inequality, and now taking summation over I equal to 1 to infinity. So summation I equal to 1 to infinity, and again here we take summation over I equal to 1 to infinity, and so let us take Q 1 over Q outside. This is I equal to 1 to infinity. Okay, so here let us take this by following 1 over P, then summation I equal to 1 to infinity. Then what we have? Is 1 over P. So this quantity, what is this quantity? So this is equal to, so this is constant, we can take it outside, 1 over P times norm X P or P, then summation absolute value of Xi power P, summation over I equal to 1 to infinity plus 1 over Q times Q norm of Y power Q, then times summation absolute value of yi power q summation over I equal to 1 to infinity. Okay, so let us go to the next page. So this is equal to summation xi yi absolute value of this, and let us take this quantity outside. This is constant, so 1 over p norm of this times y and summation over I equal to 1 to infinity, and this is less or equal to 1 over p plus 1 over q. Okay, because this summation is nothing but norm p norm of x whole power p, and this quantity is similarly q norm of y power q. Okay, so that will be cancelled out. What will remain? 1 over p times 1 over q, and by hypothesis this is equal to 1. So what we have, this implies summation absolute value xi times yi over I equal to 1 to infinity. This is less or equal to this. Okay, so this is nothing but Holder's inequality. Now, next we prove. So, before going into Minkowski's inequality, we have another remark. Let us label the remarks. Remark 1, and here we have remark 2. So if x equal to xn, n belongs to set of all naturals, belongs to LP, then what we have, then this implies, let me write in words, then the sequence absolute value of xn power p minus 1, okay, n belongs to set of all naturals, then this sequence is in LQ. Okay, for PQ in r greater than 0 with 1 over p plus 1 over q, this is equal to 1. Okay, now we prove Minkowski's inequality. So here is the statement: let p lies between 1 and infinity, and x equal to the sequence, real sequence xn, where n belongs to set of all naturals, comma, y equal to the sequence yn, n belongs to set of all naturals, belongs to LP. Then what we have, then x plus y belongs to LP, and p norm of x plus y is less or equal to p norm of x plus p norm of y. So the first item implies that LP is closed under addition, and the second item implies that this function p norm from LP to set of all reals satisfies triangle inequality in LP. Okay, so let us prove the theorem. So here is the proof. So first we prove the first item. So for x and y in LP, we will show that x plus y is in LP. So here proof. So we will use the following inequality, using the inequality a plus b whole power p less or equal to 2 power p times a power p plus b power p. So this inequality we have proved in theorem 1, where a and b, these are non-negative reals. For a and b are non-negative reals, and p belongs to 1 comma interval 1 comma open interval 1 comma infinity. Okay, so using this inequality, we have xn plus yn. So absolute value of this power p, this is less or equal to absolute value of xn plus absolute value of yn whole power p. And now here we use this inequality. This is less or equal to, so this is less or equal to 2 power p times absolute value of xn power p plus absolute value of yn power p. And this implies summation xn plus yn power p is less or equal to 2 power p summation absolute value of xn power p plus summation absolute value of yn power p, and summation over n equal to 1 to infinity, and here also n equal to 1 to infinity. Okay, and the right hand side, this is finite and this is also finite, so right hand side is less than infinity. Hence what we have, and this implies x plus y, which is a sequence xn plus yn, and belongs to set of all naturals. This is in LP. Okay, so this proves the first item. Now we prove the second item. So this is proof first item. Second item. Okay, so for x n plus yn, so absolute value of this power p, so this is equal to, one can write xn plus yn times xn plus yn power p minus 1. Okay, and this is less or equal to absolute value of xn plus absolute value of yn. So this quantity is greater than or equal to this quantity, and times xn plus yn power p minus 1, and therefore what we have, so this is equal to xn absolute value of xn times power p minus 1 plus absolute value of yn times xn plus yn absolute value of this power p minus 1. Okay, now we use remark 2. So xn, so this sequence xn plus yn, okay, belongs to LP. So now this absolute value power p minus 1, okay, this sequence is in LQ. So xn plus yn absolute value of this power p minus 1. So let's say this is equal to Zn, implies, so remark 2 implies if Zn equal to this, then this implies Zn, this sequence belongs to LQ, where Q is positive real numbers determined by the following equation: 1 plus 1 by p plus 1 by q. This is equal to 1. Okay. Now using this, so what we have, x n plus y n, absolute value of this power p, this is less or equal to absolute value of x n times absolute value of z n. So where z n equal to this plus absolute value of y n times absolute value of, so here we don't need to put absolute value, still we can put zn. Okay, now we take summation on the both side, and what we have, so now applying Holder's inequality, so put summation on the both sides, n equal to 1 to infinity, n equal to 1 to infinity, equal to 1 to infinity. Now we use Holder's inequality, applying Holder's inequality. So applying Holder's inequality, what we have, so this is the left hand side. So what is left hand side? This is nothing but x plus y p norm of this power p, and this is less or equal to this, and this is less or equal to, by Holder's inequality, norm of x, so p norm of the sequence x, so this is p norm, and q norm of z plus p norm of y times q norm of z, and this is equal to p norm of x plus p norm of y times so this is z, q norm of z. So let me write in the next page. So therefore what we get, so now let us calculate what is q norm of z. So this is equal to zn power q summation over n equal to 1 to infinity whole power 1 over q, and what is zn? Zn equal to this quantity. So this is what? This is xn plus yn power p minus 1. So this is equal to, so we replace zn by n equal to 1 to, so we replace zn by xn plus yn power p minus 1, then power q, so p minus 1 times q. Okay, so this power 1 over q, and this is equal to summation n equal to 1 to infinity xn plus yn power, so this quantity is equal to p, so then power 1 over q, and now this is equal to x plus y, so p norm of this power p and whole power 1 over q. So this is equal to x plus y, p norm of this power p over q. So now what is p over q? So let's see, 1 over p plus 1 over q, this is equal to 1, this implies p over q, this is equal to p minus 1. Okay, and so this is equal to p norm of x plus y power p minus 1. So we replace this quantity in this inequality, then we get x plus y, so p norm of P norm of this power P. So this is the left hand side, and right hand side this is less or equal to what is the right hand side, P norm of X plus P norm of Y times. So now we replace Q norm of Z Q norm of Z by this quantity. So this is equal to X plus Y P norm power P minus 1, and this implies, so this implies X plus Y P norm of this less or equal to X P norm of X plus P norm of Y. So this is the inequality we wanted to prove. Now we prove the main theorem. LP, this is a non-linear space. So proof. So in Minkowski's inequality, we have shown X plus Y belongs to LP when X comma Y belongs to LP. And the triangle inequality also we have shown, and X plus Y, this is less or equal to X plus Y. And one can, so rest of the things are very easy. So one can show that, we can show that P norm of X is greater than or equal to 0, and with and equality holds, and this is equal to 0 if and only if X equal to 0, and also, and alpha X, this is equal to absolute value of alpha times P norm of X. Therefore, we conclude that LP comma this function is a non-linear space. So we stop here.